All right, today let's take a look at derivatives of logs. So here we have our basic log function, log base A of, and then again, just like we did with exponentials, we're saying u is some function of x. So like down here, we've got just x or x squared, or, it's some function, right? The derivative of log base A of u is equal to u prime. So we take the derivative of whatever's on the inside of the log over u times the natural log of a. Okay, so the derivative of the inside of the log over the inside of the log times the natural log of a. So, for example, the derivative here of log base 4 of x is just going to be the derivative of the inside. So the derivative of x is just 1 over x times the natural log of the base. So the derivative of log base 4 of x is 1 over x times the natural log of 4. Pretty similar over here. Right? Y prime here. The derivative of the inside, so the derivative of x squared would be 2x over x squared times the natural log of 6. Now I can simplify this a little bit, right? I can cancel out one of my x's in both the numerator and denominator and just make this 2 over x times the natural log of 6. All right, so take a minute here, and you guys try numbers 3 and 4, and we'll go over them in just a second. All right, so if I want to take my derivative here, f prime of x, take the derivative of the inside, so the derivative of sine is cosine over sine times the natural log of the base, so times the natural log of 2. Right, now, we could simplify this a little bit. Right? Cosine over sine is actually just cotangent. Right? So I could make this cotangent of x over natural log of 2. Okay, so again, on a free response question where you're just writing it out, it's fine to stop here, but a multiple choice answer could look like this. Right? Then on number 4, if I want to take my derivative here, so we take the derivative of the inside, so e to the 2x. Remember from yesterday, the derivative there is just bring the exponential straight down times the derivative of the exponent times the natural log of the base, but the natural log of e is just 1, so we don't have to write that, over the inside, so e to the 2x, times the natural log of the base. So here I can simplify this sum as well. I can cancel out these e to the 2x's and just make this 2 over the natural log of 3. All right. So, just like yesterday then, if we take a natural log, okay, a log base e, something a little special, I guess, happens. So here, if we follow that same pattern, right, where we're saying we're taking the natural log, so log base e of some function of x, we take the derivative of the inside, so u prime. Then on the bottom we have u times the natural log of the base. But here my base is e, so we get natural log of e in the denominator. So what that means is whenever we have a natural log, its derivative is just u prime over u, because the natural log of e is just 1. So, for example here, the derivative of natural log of x is, well, the derivative of the inside is just 1 over x. Then we should have a natural log of e here, but we know that's just 1. So the derivative of the natural log of x is just 1 over x. The derivative here then, y prime, would be the derivative of the inside, so the derivative of 2 plus cosine of x. Well, derivative of 2 is just 0, and derivative of cosine is negative sine. So I'll just have negative sine of x in my numerator over 2 plus the cosine of x. Then we would have all of that multiplied by the natural log of e, but we know that's just 1. So this is just my derivative. Now, I cannot simplify this one any further because I'm adding in the denominator. See, I would not be allowed to take this sine over cosine and turn it into tangent, okay, because I have addition in the denominator. So don't try to simplify that. All right. So you guys take a minute here and try numbers 7 and 8. And we will take a look at those in just a second. All right. Here, my derivative will be the derivative of the inside. So the derivative of x squared plus 2 would just be 2x over the inside. So x squared plus 2 times the natural log of e, which is just 1. Then over here, my derivative will be the derivative of the inside. So the derivative of tangent is secant squared over the inside. All right. Now, there are lots of different things that we could do to change this. We could turn everything into sines and cosines. We could do a lot of manipulation with this. So I'm not going to explore all the different things we could do here. All right. But one other thing that commonly comes up then when we talk about derivatives of logs is, well, what's the domain of these derivatives? All right, so for, let's see, for number 5, we said our derivative was 1 over x, right? Well, what's the domain of that function? So the only place, okay, and this is going to be the common for logarithmic derivatives, we always end up with something in the denominator, right? Well, in order for a function to exist, we can't have 0 in the denominator. So that's going to be the common theme here. The domain is just going to be wherever the function does not have a 0 in the denominator. So what we can do is say, well, here, my denominator is just x, right? I want my denominator to not equal 0. Well, we already have x by itself, so we know that our domain is all values except 0. So if we want to write that in interval notation, we would say negative infinity to 0, not including 0, union 0 to infinity. Okay, that's how we would write that in interval notation. We can do the same thing with the rest of our derivatives here. For number 6, our derivative was negative sine over 2 plus cosine. So again, we want to see, well, where is my denominator going to equal 0? So I want to say 2 plus cosine cannot equal 0. All right, so then I could subtract my 2 over and say, well, cosine of x cannot equal -2. So what I want to find is, well, what values of x here would make this equal to -2. So cosine of what equals -2? Well, there aren't any values, right? The range of cosine is just -1 to 1. Right? If you think about on the unit circle, going around the unit circle, the largest value we can get for cosine is +1, and the smallest value is -1. So there's no possible value I can plug in here to get -2. Right? That means that there's nothing that I can plug in to get a 0 in the denominator. So our domain here is just all real numbers. Our domain would be -infinity to +infinity, okay, because I get no answer here when I set the denominator equal to 0. So there's nothing that would make this function discontinuous or an asymptote or something like that. Then number 7, we had our derivative to be 2x over x squared plus 2. So again, set my denominator equal to 0, say it can't equal 0. So we get x squared equals -2. If I take the square root of both sides, we get the square root of -2, which isn't a real value. Right? So again, there are no values that make the denominator 0. So again, in this situation, we would have -infinity to +infinity for our domain. Right? We're actually going to skip the domain for number 8, right? Because you're just not going to be asked for anything like that on the AP test. So let's take a look at a few that are a little bit more complicated, right? Just throwing in some product rule, some quotient rule, some chain rule, that kind of thing into our derivatives of logs. So let's go through this first one together, and then I'll have you guys try a few here before we go over them. So for this one, this is product rule, x squared times the natural log of x. So my derivative will be the derivative of the first, so 2x times the second, so times natural log of x, plus the first times the derivative of the second. So the derivative of natural log of x is going to be the derivative of the inside over the inside. So x squared times 1 over x, I can actually clean that up a little bit and just say my derivative then is 2x times the natural log of x plus, this would be x squared over x, right, which would just be x. So we end up with 2x times the natural log of x plus x for my derivative here. And now, again, I mean, you could see different forms of this for a multiple choice answer. I mean, you certainly could just see this, or you could see an x factored out. It could be written like this. All right, so we just need to make sure we're comfortable with that algebra to move back and forth between different forms. All right, so now you guys take a minute or two and try 10, 11, and 12. All right, and then we'll come back and go through them here in just a second. All right, let's take a look at number 10 here. So on this one, we do have, we have product rule and chain rule. So my derivative here will be derivative of the first, so the derivative of cotangent is negative cosecant squared times the second, so just times log base 5 of x squared plus 1 cubed. then plus the first, so plus cotangent of x times the derivative of the second. Right? So here, log base 5 of x squared plus 1 cubed, we'll take the derivative of the inside, so that's going to be 3 times x squared plus 1 squared, then times the derivative of the inside, right? So times 2x. Right? So that we had to use chain rule on that part. Then just over the inside, so over x squared plus 1 cubed times the natural log of the base, which is 5. All right? So we could clean this up a little bit. Right? I could cancel out 2 of these factors, right, just to make it look a little bit nicer. Right? But I'm not going to write all that out again. All right, so let's take a look at number 11. So on this one, we have a little bit of quotient rule. So here, my derivative f prime of x. So the first thing in quotient rule, square the denominator. Bring that denominator straight up, times the derivative of the numerator. So the derivative of natural log of x is 1 over x minus the derivative of the denominator, which would just be 1 times the numerator. So times natural log of x. Okay, and this one is pretty easy to clean up. Right? This one, x times 1 over x is just 1. So I just get 1 minus the natural log of x over x squared, if I clean that one up. Then number 12, this one, we're going to have to use chain rule again here. So, so the outermost function is a log, so I'm just going to have derivative of the inside over the inside times the natural log of the base. So the derivative of the inside, okay, well, if I'm looking at this inside here, right, I'm just going to rewrite this inside over here like this. So we've got cotangent of 2x plus 1 squared, right? If we write it like that, it's a lot easier to see the layers, okay? And we can see that this square is the outermost layer. So when I'm taking that derivative, my derivative will be 2 times the cotangent of 2x plus 1 to the first power now, right? So I don't have to write the first power. Now my next layer is cotangent. So now times the derivative of cotangent, which is negative cosecant squared. So times negative cosecant squared of 2x plus 1 times the derivative of my third layer. My third layer is this 2x plus 1, so its derivative is 2. And that's all going to be over then the inside, which is just cotangent squared of 2x plus 1 times the natural log of the base. Okay, so again here I could clean this up a little bit, and I'll go ahead and write this one out. So I've got 2, a negative 1, and a 2 in my numerator here, so I'll have negative 4. Now I can cancel out one of these sets of cotangents, right? I've got cotangent of 2x plus 1 and cotangent squared of 2x plus 1. So I can cancel one of those out. And I'll just have negative 4 cosecant squared of 2x plus 1 over cotangent of 2x plus 1 times the natural log of 11. All right. So let's take a look at a couple of final problems here. Right, we can always throw in equations of tangent and normal lines. So here, My function is just natural log of x, and I want to find the equation of the tangent and normal lines to that at x equals e. So to find the equation of a tangent line, I need the slope and I need a point. So let's find the slope first. To do that, I need to find the derivative. So the derivative of the natural log we know is 1 over x. And I want to figure out the slope at e. So y prime of e is just going to be 1 over e. So that's my slope at this value. I also need my y-coordinate. So to get my y-coordinate, I'm going to plug e into my original function. So that will be natural log of e. Well, natural log of e is just 1. Right? So the information I've collected is that my slope is 1 over e at the coordinate point e1. So my tangent line then will be y minus 1 equals 1 over e times x minus e. My normal line then is the same thing, just the opposite reciprocal slope. So y minus 1 equals, that would be negative e over 1 times x minus e. Right? And our last problem, this one is a little bit different. Okay, this one's kind of strange to think about. And we're given a lot of information here. So it says a line with slope m passes through the origin. So the origin we know is the point 0, 0, right? And is tangent to y equals natural log of 2x. We want to figure out the value of the slope. So we're not really given a lot of information here. Okay, we're not given a slope. We're not given the point that it hits our curve. All we're told is that this tangent line goes through the origin. So what we can do here, okay, if I know that my tangent line goes through the origin, right, and I'm thinking about my line is y equals mx plus b, okay, well, if it goes through the origin, my b is 0. I know that. So I can write my line as y equals mx. Excuse me. Now, I can go ahead and, well, let's do this first. I can solve this for m, right? So I can say, well, if I divide both sides by x, that y over x is equal to m. That's going to come in handy here in a second. So here, okay, I know that my slope, my m, is going to be whatever the derivative of this is. So if my original function is natural log of 2x, its derivative, y prime, will be the derivative of the inside over the inside. And I can cancel out that 2, or those 2's, and just make this 1 over x. So my y prime, that's the same thing as m, my slope, right? So I can say that m is equal to 1 over x. Well, now if we look here, I've got 2 different equations for m. Whenever we have something like that, I can set those equal to each other. Right? I've got this equation solved for m, this one solved for m. That tells me that y over x will equal 1 over x. Right? And then I can solve this equation, right, for y. It's pretty obvious looking at this equation that y would have to equal 1. Right? Well, if y equals 1, I can go back to my original equation here to figure out what x is going to be. So 1 is equal to the natural log of 2x. Now to solve something like this, right, we want to raise both sides to whatever our base is, right? So this is log base e. That means I'm going to raise both sides to a power of e. Right? So here I just get e to the first power equals, well, e to the log base e of 2x is just equal to 2x. And then I can divide both sides by 2 and get that my x value is e over 2. So what we've found so far, right, is that the coordinate point where this line is going to hit my curve is at e over 2, 1. But that doesn't answer the question yet. I still want the value of m, the slope. Well, what I can do now, okay, I can say I want y prime of e over 2. Right? So I know that y prime is equal to 1 over x. So y prime of this x value of e over 2 is just going to be equal to 1 over e over 2, which would just be 2 over e. And that answers the question, right? That would be the value of m. That would be the value of the slope. Okay, so this, I know this one was a tricky, complicated, not super intuitive problem, okay? But there are 2 problems like this on your Math Excel, right? So give them a try. Try to go through this process. The process is going to be very similar for the problems on the Math Excel, all right? So that's it. That's the entire lecture. Go ahead and give the Math Excel a try now.